Okay, good morning and welcome to the Deeper Talk session here at the Sanford Lab Homestake Visitor Center. Today, we will have three speakers talking today, and following that, we will have a Q&A period following the presentations. For our online audience, please use the Q&A form that's on the Vimeo website. And in person, please wait until the end. We'll have a single Q&A session for all three speakers. This talk will also be recorded and will be available to review using the same link you received to join this talk, as well as being on the institute.surf/Deeper Talks website. Our three speakers today, in order of their presentations, we're going to start with Dr. Julie Geerlein. She is an assistant professor in the physics department at Colorado State University, and her expertise is in theoretical particle physics, with her studies centering around the most elusive particles of the universe, neutrinos. Before joining Colorado State University, she was a senior research fellow in the theoretical physics department at CERN and a research associate at Brookhaven National Laboratory. And she obtained her PhD in 2019 from the Autonomous University of Madrid, Spain. After that, we'll have Dr. Bhupal Dev. He is an associate professor of physics and a member of the McDonald Center for the Space Sciences at Washington University in St. Louis. He got his PhD from the University of Maryland in 2012. Then held postdoctoral positions in the UK and Germany before joining Washington University in 2016. He's also a recipient of the Fermilab Intensity Frontier Fellowship and the university's Research Association Visiting Scholars Award. Finally, we'll have Dr. Borut Bach. He is a professor at the Josef Stefan Institute in Ljubljana, Slovenia. After his PhD at the University of Ljubljana in 1994, he continued his research in Durham, Trieste, and New York, before getting his current position in 2002. His main focus of research is in the grand unification of elementary forces, and he has worked on various theoretical and phenomenological aspects of particle physics and cosmology. For example, heavy quark effective theory, symmetry, non-restoration in the early universe, supersymmetry, the ADS CFT correspondence, and asymptotic safety. And with that, I will let you take over and enjoy.
Okay, thank you very much. It's a pleasure to be here and talk to you today about nature's ghost particles, neutrinos, and how we test them in the lab. So what is a neutrino? The name comes from Italian. It means small neutral one. And this also accurately describes the characteristics of a neutrino. Namely, it is electrically neutral, which means it is unaffected by electric or magnetic fields, unlike electrons, which means neutrinos do travel on a straight line. You cannot deviate them from their path with any electric or magnetic fields. As far as we know, there are three types of neutrinos, which we call flavors. They're called electron, muon, and tau neutrino, and they're part of the standard model of particle physics. They are point-like particles, which means they cannot be split into subcomponents. They have no substructure. And as you can see here, neutrinos, and I particularly also point out the gauge bosons, the force carriers with which the neutrinos interact, which are called C boson and W boson, and these are essential to produce and to detect neutrinos. So neutrinos are produced and detected via the weak process mediated by these W and Z bosons. We produce them in a lab via the decays of heavy composite particles like a neutron or a pion, which are composed of elementary particles called quarks. We produce neutrinos in the lab, for example, via reactors, so reactor neutrinos, where we are looking at nuclear decay processes, which then lead to a lot of neutrinos, but we can also produce neutrinos in accelerators, and this video shows you how we do that. Okay, so how do we detect neutrinos? We detect them by letting them scatter with electrons, nucleons, or quarks in a detector material. There are two ways we detect the neutrinos, either via neutral current processes or charged current processes. The way we identify the neutrinos or what the signal is in these processes is the scattered or produced particle after the neutrino scattering. And in particular, in this charge current interaction mediated by W boson, an electron neutrino will produce an electron in the final state, a mu neutrino, a muon, a tau neutrino, a tau, which allows us to distinguish these different flavors, these different types of neutrinos experimentally. So we have many neutrino sources, and indeed, neutrinos are basically everywhere. However, they react only very, very rarely. Indeed, 100 trillion neutrinos flood through you per second, but the chance that a neutrino interacts with your body at some point in your life is only 1 out of 4, which means neutrinos interact very, very rarely, which begs the question, how do we actually detect them? And the answer is, we just need to increase the probability of interaction, which means we build huge detectors. And two examples are shown here, the Super Kamiokande detector, which is based in Japan, and the NOVA detector, which is based in the US. And here in yellow, I show two people in comparison to the sheer size of these detectors, which for Super Kamiokande has the size of the Statue of Liberty, is also 3,300 feet underground. The NOVA detector weighs the equivalent weight of 7,000 elephants, and it's longer than 2 blue whales behind each other. So these are huge, huge detectors, and we need them because neutrinos interact so rarely. Nevertheless, we achieved to detect neutrinos. In fact, the first solar neutrinos, which are neutrinos produced in the sun, were detected here at SURF by Ray Davis in the Homestake experiment. And for this detection, he is also awarded a Nobel Prize in 2002. However, what he saw was only 1/3 of the theoretically predicted neutrinos were observed. This really came as a surprise because this also laid the ground for the discovery of neutrino oscillations, which is the fact that neutrinos change their flavor, their type, when they propagate over a distance. For example, an electron neutrino can transform into a muon neutrino. The probability of change depends on the neutrino energy, the distance they travel, as well as the fundamental neutrino parameters. We have seen neutrino oscillations already in several experiments, and which means we could learn about the neutrino parameters. Here are two examples of an experiment in China as well as another experiment in Japan, and you really see this oscillatory behavior as a function of distance the neutrinos travel divided by their energy. So we already learned about many of the fundamental neutrino parameters, but we still don't know all of them. To learn more about neutrinos, we have to build new optimized experiments to measure them, and the Deep Underground Neutrino experiment, which is currently under construction at SURF, is one of these experiments. As you have seen, these neutrino experiments are huge, so we need actually very, very big space for them. And only recently, the cavern for the dune detector has been fully excavated here at SURF. So similar to what I showed before, how do you produce a neutrino beam? This also happens for the dune experiment. These neutrinos are produced in Illinois at Fermilab close to Chicago by colliding protons with the target. Then we produce unstable particles like pions, neutrons, kaons, which decay into neutrinos. The neutrino beam then travels 800 miles to SURF, where the neutrinos then scatter with a liquid argon detector. We expect around 10 neutrinos per day. And of course, what we are going to see in the detector is the produced particles, electrons, muons, or even tau leptons. But you will also see other sources of neutrinos apart from these accelerated neutrinos, like neutrinos produced in the atmosphere, in the sun, or even via supernova explosion. By then comparing the neutrinos detected in South Dakota to the neutrinos produced in Illinois, we can learn how many neutrinos how many of the produced mu neutrinos are still mu neutrinos, or how many of them have transformed into a different flavor of neutrinos. In the end, we will learn more about the unknown fundamental neutrino parameters with this experiment.
All right. So we heard from Yulia about neutrinos coming from man-made sources like reactors and accelerators. So now we're going to switch to natural sources of neutrinos. So neutrinos are everywhere, as you heard from Yulia. They are produced in various different ways, and some of the natural sources of neutrinos, they're actually very familiar to you, like this. I just ate a banana today, so I might be emitting some neutrinos, but they're harmless. Don't worry about it. You get many more neutrinos coming from the Earth's interior. They are the geoneutrinos from the nuclear reactions or the unstable radioisotopes that are decaying. And also you get neutrinos coming from the atmosphere. These are the neutrinos produced from the cosmic ray showers. So the cosmic rays hit the upper parts of the atmosphere, and then they produce charged particles, unstable particles like pions and kaons and so on, and they decay, and from that we get neutrinos. We also get lots of neutrinos from the sun. Sun is a nuclear reactor, it's a fusion reactor. In that process, while generating energy, it also produces lots of neutrinos. And then we have even more violent processes producing neutrinos, like the supernova explosion. In fact, 99% of the energy from the supernova explosion that is emitted in the form of neutrinos. And even more cataclysmic processes like this active galactic nucleus. This is the place where stars are born. You have a black hole at the center, and then gas and dust, there's circling around, being gobbled up by the black hole. And in the process, you emit very high energetic particles, among them also high energy neutrinos. So as you can see here, we have a wide range of sources for the neutrinos, and in fact, they cover a wide range of energy, about 20 orders of magnitude in energy. Okay? And this is kind of unique to the neutrinos. Only other thing that does this is photon. So in that sense, neutrinos serve as a good messenger for all these different astrophysical processes. So you can forget about the y-axis here for the timing, just focus on the x-axis. And as you can see, we have neutrinos coming from a very, very small low energy here, which is the Big Bang neutrino. They are the relic neutrinos coming from just like 1 second after Big Bang. And then we have all this terrestrial, solar, atmospheric, and then when you go to very high energies, you get all the astrophysical, both galactic and extragalactic neutrinos. And so how do you detect all this? Well, we have to build experiments. And in fact, people have built many experiments, and they're currently building many more experiments to detect these neutrinos. So obviously, I won't have time to go into all the details of this. For example, for the relic neutrinos, it's very hard to detect because their kinetic energy is very small. So when they interact with some nucleus, the recoil energy will be very, very small to be detected. So these very hard experiments, but people are still trying. So I'll mostly focus on the higher energy side, starting from the solar, atmospheric, and then go to the high energy neutrinos. Okay, so for the solar neutrinos, as you heard from Yulia, we are getting about 65 million neutrinos per second just in our thumb coming from solar neutrinos. In fact, as one of the pioneers in this field, Hans Bethe, he said that this is most important reaction for all life. You have like 4 protons going into helium-4, and in that process we emit neutrinos. In the 1960s, this was actually one of the biggest puzzles, which is called the solar neutrino puzzle. Well, for some reason you can't see the text over there, but the idea is that how do you detect the solar neutrinos? Well, so Ray Davis, he set up this experiment right here in the Homestake mines, and he just filled the cavern with about 100,000 tons of 100,000 gallons of dry cleaning liquid, and so you have chlorine in that. So when the electron neutrino comes from the sun, it hits the chlorine and produces an argon, and then you just take out the argon, then count the argon, because argon is radioactive, argon-37, it decays about, its half-life is about 35 days, so you just count the number of argons. It's a counting game. And again, as Julia mentioned, the neutrinos are very shy, they don't interact much. So we need large volume, and you have to wait for a long period of time to detect. So this is where patience pays off. Ray Davis, he was very patient. He performed this experiment. Over many, many years, and at the end, what they found is very surprising. So this is the actual data from one of the papers, which shows that the average number of neutrinos they detected from the sun were actually one-third less than that was predicted from the solar model. So this was a big puzzle known as the solar neutrino puzzle, and there are many, many different ideas people propose to solve this, but eventually now we know that the actual solution comes from neutrino oscillations. Okay? And so neutrino oscillation is a purely quantum mechanical phenomenon. If neutrinos are classical particles, you will not get these oscillations. So this is again another vivid illustration of the power of quantum mechanics in play. Okay? So it has practical implications. And so what is neutrino oscillation? Well, so neutrinos they live in superposition of different states. So you start with, let's say, an electron flavor, one flavor of the neutrino, but then over time, when they can oscillate into a different flavor, just because they are in superposition of different flavors. Different mass eigenstates. So for example, you start with electron neutrino in the sun, and then over, this is L over E. L stands for the baseline length, and E for the energy of the neutrino. So for a given baseline length and for a given energy, they can oscillate into a different flavor. For instance, the probability of the electron neutrino remaining electron neutrino, it decreases over time, and then again it increases. So that's the oscillation effect. So if you're doing the experiment over at this baseline, for example, then you would not see as many electron neutrinos as you would have expected coming from the sun, and that's part of the solution to the solar neutrino puzzle. Of course, this simple picture is valid only in vacuum, but we know that the neutrinos coming from the sun, they are coming through matter from the solar interior. So there are some other complications there, but let's not go into that in detail unless one of you have questions on that. Anyway, so this is also observed in other places. This is also observed in the atmospheric neutrinos. The same oscillation phenomenon. So what happens is that you have the high energy cosmic rays, mostly protons, hitting the nucleus, let's say nitrogen or oxygen nucleus in the upper parts of the atmosphere. You produce charged particles like pions and kaons, and then they decay to muons and to neutrinos, and then the muons further decay, and in that process you produce, for example, you produce the muon neutrinos and also electron neutrinos, right? Now you can look for them, and in fact that's what the superconductor collaboration did. They set up this experiment in superconductor detector, and what they found is very surprising again. So so they look for the oscillation phenomenon for both the electron and the muon neutrinos, but it turns out that the electron neutrinos, they don't oscillate. So for that given baseline, for the atmospheric neutrinos, the electron neutrinos don't oscillate. So you can see here the theoretical prediction and without oscillation is exactly matching with whatever data they get. But now for the muon neutrino, that's not true. For muon neutrino, what they find is that without oscillation, you don't match with the result, but with oscillations, you perfectly match with the data that you have. So that is another clear way to see that the muon neutrinos do oscillate for atmospheric neutrinos, and the muons mostly go to tau neutrinos, it turns out. And they can also do a bit more, more detailed analysis here, because the atmosphere is all around the Earth. So, and the neutrinos, they can directly go through the Earth. So what you can do at any given moment of time, you're getting the neutrinos from from upper part of the, like from above, you're also getting the neutrinos from below, right? And the baseline is different, because the neutrinos coming from above, they are having only, like, have about a few kilometers of atmosphere, but the neutrinos coming from below, they have the few kilometer atmosphere plus the whole Earth, the Earth's diameter, which is about 12,000 or 13,000 kilometers. So due to this different baseline, you can do different measurements, and then you can actually tell that indeed, for you can study the oscillation phenomenon in a lot more details, and that's what is shown by this by the distribution. So this cosine theta stands for just angle with respect to the zenith. Okay? Now, why this is a big deal? Well, this is a big deal because if you just look at the probability, what you find is that the survival probability, it depends on two important parameters: the mixing between the different flavors, and it also depends on the mass square difference between the different mass eigenstates of the neutrinos. Now, you know that the sign of a quantity can be non-zero only if the quantity is non-zero. So that means that both the mixing angle and the mass square difference have to be non-zero to make this oscillation work. And that's a big deal because in the standard model of particle physics, as we know, there is no mixing, there is no mixing between the neutrinos, and therefore this is the first ever direct evidence for physics beyond the standard model. And so far, this is the only conclusive laboratory evidence for physics beyond the standard model. That's the reason why the neutron oscillation is really big deal. Okay, so now let me move on to other exotic sources of neutrinos, like the supernova neutrinos. So in 1987, February, people saw this supernova explode in the Large Magellanic Cloud, which is about 50 kiloparsec from us. It's a satellite galaxy of the Milky Way galaxy. So this is the optical image actually coming from the Anglo-Australian Observatory, and this is the before the supernova burst. It looks like this, and after the burst, it looks like this in optical. So you can clearly see that you're getting this supernova burst, and at the same time, very luckily, there are detectors built for other purpose, and they observe the neutrinos coming from the supernova. For the first time in human history, we got these neutrinos from supernova. Okay, but there are only a handful of neutrino events because the detectors were not big enough. But still, they could get these neutrinos, and they could do some studies on the stellar properties, on new physics, and so on. And in the future, for example, with the Dune experiment that's being built here, you would get many more neutrino events if such a supernova goes in the near future in the galaxy. For example, if a supernova 10 kiloparsec goes off after the Dune experiment is built, then you get this kind of events. You would get like about handful, not handful. You'll get about actually hundreds and thousands of events depending on where the supernova is burst. So this will give us much more information about the supernovae. And also, this is good news for physics beyond the standard model, because the same particles that could solve some of the mysteries of the standard model could also be emitted from the supernova, and they take away more energy. And as I told you before, 99% of the energy goes in neutrinos. So if some other particle is sharing that energy, then you would not see the same luminosity as we would expect in the standard model. So from there, you can put some bounds, or you can actually search for new particles. So that's why it's important. Okay, so in the last part of my talk, let me go to the higher energy part of the spectrum and talk about astrophysical neutrinos. Now, these neutrinos are actually a messenger for very extreme astrophysics. And the reason is that the only messengers we have so far are the cosmic rays and the photons, and now recently gravitational waves. But the problem with cosmic rays is that they're charged particles usually, and the charged particles, they can be bent in magnetic fields. So we really we cannot get directional information by just looking at the cosmic ray. You cannot tell where it's coming from because it might have gone through many scatterings and absorbed some deflections and so on. And similarly for gamma rays, the gamma rays can be, they can lose their energy through cascades. They can, they can also scatter, get absorbed in the intergalactic medium and so on. But neutrinos, because they're too shy to interact, they just come straight to us from the source. So they can serve as a very good astrophysical messenger for processes that's happening way far out there. And experiments like IceCube, which is built at the South Pole in Antarctica, so they were built just to see these astrophysical neutrinos, and in fact they were successful. About 10 years ago, 10 to 12 years ago. So they detected the first astrophysical neutrinos, and now they have actually thousands of such events. And this is important from another point of view, that this is the birth of what is called the neutrino, like high energy neutrino astrophysics. So the same process that gives you the neutrinos, like the pion decay, will also give you photons. So this is the origin of this multi-messenger astrophysics, that you have a strong connection between the flux of neutrinos you get, and also the flux of the gamma rays, and also the flux of cosmic rays. So they are all connected to each other. Okay? And in fact, IceCube for the first time 2 years ago detected both neutrinos and gamma rays from the same source. Okay? So this was a this was an active galactic nucleus called NGC 1068, and for the first time they detected both neutrinos and gamma rays. And you can use this to study the astrophysics of the active galactic nuclei and such sources. You can also do fundamental physics with this kind of observations. For example, we don't know the nature of the neutrinos. As we'll hear in the next talk by Boruth, the neutrinos can be either Dirac particles, they're their own not their own antiparticles, or they can be Majorana particles, that means they're their own antiparticles. Or they can be somewhere in between. For example, they can have tiny bit of Majorana-ness, but they can be mostly Dirac. So in that case, what would happen is that the active neutrino can oscillate into a sterile neutrino, and by the time they reach us, if they have oscillated into sterile, then we lose part of that flux. And so as we recently showed in one of the papers, you can use this as the multi-messenger neutrino astrophysics to actually probe this nature of the pseudo-Diracness of these neutrinos. Okay, so the future of this field is really bright. There are many other neutrino telescopes are being proposed or going to be built. I mentioned about IceCube. There's a proposal to do IceCube Gen 2, which is a higher, like instead of 1 kilometer cube, we have 10 kilometer cube volume. There are also other detectors like the P1 or the KM3 network. They're being, one of them is being built actually right now. And also connection with the multi-messenger physics is getting more and more attention. And now there is a proposal to do simultaneous observations of cosmic rays, photons, gravitational waves, and neutrinos. This is called the multi-messenger observatory network. So we'll learn a lot about the workings of the universe from these multi-messenger observations. So in conclusion, neutrinos have opened a whole new window into the universe. Thank you.
So, okay. So let's start the boring part of the talk. So let me say something about the masses in the standard model. So we know that in the standard model, there are we have 4 left-handed type of quarks per generation: the up quark, the down quark, the charged lepton, and the neutrino. This is the hero of our talk. And then there is a right-handed part, which has only up quarks, down quarks, and charged leptons. So there is no right-handed neutrino. We have 3 interactions, SU3 cross SU3 cross U1. You don't need to remember that, but just remember that there are 3 of them. And I stress again, there are pairs, up, down, and quark, and charged leptons come into with pairs, okay? But there is no right-handed neutrino, so there is only one single left-handed neutrino. So how do mass, what is that? So how do mass appear in the standard model? At the Lagrangian level, we have, the masses are 0. So what gets broken in the standard model is the gauge symmetry. And this is due to the Higgs vacuum expectation value. The Higgs vacuum expectation value is non-zero and is around 100 GeV. Oh, that is impossible to continue. What's going on? No, also, this is the old file. Oh my God. So there are 3 Ukavas in the standard model: the up, down, and charged leptons. And due to the Higgs non-zero wave, this is also the old file. It's not the new one. Actually, this is the first one. It's not even the second or third. that should be, this is there. Thank you very much. So let's go back to the how the masses, charge Fermi masses are we get from the in the standard model. So as I said here, the VEV 100 GeV, around 100 GeV of the Higgs is the only mass scale in the standard model at the classical level. That means that if we can describe some masses, they must be proportional to this vacuum expectation value. So the up, down, and charge lepton masses are proportional to this VEV. And the proportionality factor on top of that, there are these Yukawa couplings that accommodate the different masses in this of these different particles. I remind you that the linear dependence of the mass on the vacuum expectation value is crucial. For that to be true, it's crucial to have particles in pairs, so the left-handed and the right-handed ones. Since there is no right-handed right-handed particle neutrino in the standard model, neutrino remains massless. However, we know experimentally that neutrino has at least two neutrinos, we heard from Bhupal, are non-zero. So there are two ways of how giving mass to neutrino on top of the standard model. So you first thing is completely obvious. You just add the right-handed neutrino. So if you add this right-handed neutrino, you can write the same type of mass as you wrote for the other charged fermions. It's important to know that this term conserves lepton number. Okay, this is to remember. Another possible way is to add another high scale to the standard model. So at the high ultraviolet scale, some new physics will appear, and then the neutrino can be written as a ratio of a square of the VEV and this new scale. This mass, however, is different and breaks lepton number. Okay, so is of different type. This type of mass is possible only because neutrino is electrically neutral. Such a mass cannot be written for the other charged fermions. Now let's summarize. The standard model predicts massless neutrino. To describe masses, we have to add a right-handed neutrino. One possibility is to add a right-handed neutrino. In this case, we talk about a Dirac neutrino. So this is a Dirac neutrino, which and the theory is invariant under lepton number. Another possibility is to break lepton number. In that case, the Majorana has the neutrino has a Majorana mass. So from here, we don't know whether neutrino are Dirac or Majorana, or only experiment can tell us. So this is done by can be looked at neutrino as double beta decay, which is essentially the neutron-neutron going to proton-proton and electron-electron. So this clearly breaks lepton number. If we will ever find such a process, that means that the neutrino is Majorana. Can we do better in a theory? From a theoretical point of view, we could do it better. We could predict whether neutrino is Dirac or Majorana. First, let's decide what is our theory beyond the standard model. To motivate grand unification, let's remember that the standard model has 3 gauge interactions instead of 1, so it's not very economical. It has 5 different fermion types instead of 1, again non-economical. And there is no explanation why the electric charge is quantized. We know from the measurement, very precise, that the electron charge is 3 times the down quark charge. The up quark is twice the down quark charge, and so on. And this is unexplained in the standard model. Now, how can this be improved? Well, we can embed the standard model into grand unified theory. Let's take an example. Let's say the SO10 grand unified theory. And this immediately tells us these 3 points. First, there is only 1 gauge interaction, exactly SO10. So not 3 as before, but 1. There is 1 type of elementary fermions. All 15 fermions of the standard model are included here, but there is an extra particle which is predicted, and is the right-handed neutrino. Finally, since there is an only single gauge group, charge is automatically quantized. So this is already built in. Now, there are other consequences of grand unified theories. One is that proton and neutron are unstable, and they decay with a very large lifetime. This is the experimental limit, and there are some predictions around these numbers. The second consequence of the GATT is the existence of new objects, which we call magnetic monopoles, and they are directly related to the quantization of charge. And finally, there are relations among fermi masses that I will focus in the next 2 slides. First, is the presence of the right-handed neutrino that we predicted in SO10, does that tell us that neutrino is a Dirac particle? The answer is no. If it were, if it were like that, such an SO10 would not describe the standard model in the low energy, but it would be a different, more complicated model. So we automatically come to the second possibility, where the neutrino is Majorana, and the relation for this mass is v square over m. So it's the quadratic in the VEV. And so in SO10, what happens? As I said, neutrino must be Majorana, and lepton number is not conserved. Second, the new scale m that is connected to the grand unification scale, which is huge, tell us that neutrino mass are much smaller than the charged Fermi masses. And finally, we saw 2 different origins of masses. One was the quark masses was like linear in the VEV, and the neutrino mass has a completely different origin. It's quadratic. So it is not so difficult to accommodate at the same time small quark mixings, but large neutrino mixings, as we know from experiment. Thank you very much.
Okay, thank you for all that. If anyone in the audience has a question, please raise your hand and I'll bring the mic over to you. Otherwise, if there are any questions from online, please let me know, Stephen.
You talked about neutrino-less double beta decay as testing this conservation law. Are there other ways of testing this conservation law other than neutrino to establish that neutrinos are Majorana fermi?
Maybe you have some comment on it.
Well, I mean, the other one would be the connection between baryon number and lepton number. So if you observe the baryon number violation, we might get some insights into also lepton number violation. But yeah, as Boris said,
baryon number is very much conserved, much more, right?
So I was wondering that, is there like, I mean, this is more like a, I'm just thinking through, is there like any, like a grand strategy, like to, like the spin 10 group that you got there? So you're kind of, you know, usually they're trying to embed this standard model group into that. Is there like a strategy to kind of like extend these groups the more and more, so that to find bigger groups and see if you can embed them and then do whatever?
Yeah, in principle, historically, people studied with SU5, but SU5 is not a good theory of neutrino mass, so that's why I didn't mention that. On top of that, for example, this SO10 you can embed in E6. That is particularly, I mean, this is has some good point. For example, but they are very technical. So yeah, there are you could embed even big groups into bigger groups. But with the E6, more or less, you finished. This is an exceptional group, and higher exceptional groups do not have chiral fermions, which are necessary for the standard model.
You mentioned how neutrons and, excuse me, will electrons decay as well?
Electrons, no.
No.
Not in these theories.
Okay, and we have one question from online from Tom. What are the expectations of Dune and LBNF for reconciliation of the neutrino theories?
So, I mean, there are different types of neutrino theories. I mean, Worod was talking about some of them, theories which try to explain the origin of neutrino mass. And one of the important, like, the first question is, are neutrinos Dirac or Majorana neutrinos? And as we've just discussed, a way to answer this question is via neutrino-less star beta decay. Now, Dune will not be a detector or an experiment which will be sensitive to neutrino-less star beta decay. However, there are a couple of experiments which are explicitly looking for neutrino-less star beta decay. So far, we have not seen neutrino-less star beta decay. However, there's still a large region of parameter space available. So we don't know yet if neutrinos are Dirac versus Majorana. So this is one type of neutrino theory. Another type of neutrino theory is, for example, theories which try to explain these fundamental neutrino parameters, these mixing angles and these mass splittings, which are essential in the calculation of the neutrino oscillation probability. Since Dune is going to measure the oscillation parameters very precisely and will also measure all of the oscillation parameters, including a phase, which can lead to CP violation, which means that neutrinos and antineutrinos behave differently. Some neutrino theories which explain or try to find a rationale behind these fundamental neutrino parameters can be tested by Dune by this more precise measurement of the fundamental neutrino parameters. So yeah, Dune will bring us a step closer to maybe understanding more about neutrino and neutrino theory, but will not answer all of the questions we have. But there are other experiments in place which will hopefully answer our remaining questions.
So I had a question about the proton lifetime mass that you mentioned for SO10. How natural a prediction is that? If tomorrow the sensitivity to the proton decay lifetime increases and goes beyond this, does that conclusively rule out the theory, or can it be tweaked to, give a larger lifetime prediction?
So the lifetime is proportional to the fourth power of the scale at which the gut theory appears. And that means it's a very strong dependence. How we determine that scale is through a very logarithmic, there are other ways, so through logarithmic running of the gauge couplings. And that has much bigger uncertainties. So I would say that on one side, we determine the scale with a logarithmic precision, but then we have to predict the lifetime with a power law. And so I don't, well, in other words, what I want to say is that quantification cannot tell very precisely what the lifetime is. So you can fail by one order of magnitude very easily. It's part of the uncertainty.
So I have a very naive question. So I know some of the new physics models assume the existence of the heavier the neutrino, like a fourth generation neutrino. So would the delta CP measurement, for example at Dune, address this possibility?
Yes, partially. So Dune will also be sensitive to the presence of another generation of neutrino, the sterile neutrino, and it will be sensitive to this sterile neutrino depending on its mass. So a very light sterile neutrino, like an EV scale sterile neutrino, will really show up as a new oscillation frequency. If you have a sterile neutrino which has a mass MeV to GeV, it can be produced in the pion decays and meson decays. So you will see a different decay spectrum when you produce the neutrinos. You can already see that in the near detector. And finally, if you have a very heavy sterile neutrino, very heavy meaning basically heavier than the GeV scale, you cannot produce it anymore kinematically in the meson decays, but it still has an impact because the neutrino mixing matrix, the PMS matrix, will not be unitary anymore. I mean, the 3 times 3 neutrino mixing matrix we are sensitive to will not be unitary anymore. However, the mixing matrix, including sterile neutrino, this will of course still be unitary. So we can do unitarity studies at Dune to also be sensitive to a sterile neutrino. And finally, a sterile neutrino, like one generation of sterile neutrino, will also introduce new CP violating phases, and you might even mix up the CP violation coming from either our delta in the 3-flavor framework or these new CP violating phases. So yeah, Dune will be sensitive to sterile neutrinos in different ways depending on what their characteristics are, which is of course very interesting and also complementary with the whole short baseline program happening at FermLab, which are more targeting the what light sterile neutrinos, the 1 EV sterile neutrinos, motivated by all of the light sterile neutrino anomalies. Yeah, exactly. So to really figure out if there is a sterile neutrino and how many sterile neutrinos there are, you really have to do a fit to the whole Dune data set, or maybe even would be best to also include like data sets from other oscillation experiments. And then if one sterile neutrino fits the data best, then you know it's probably just one. If 3 sterile neutrinos fit the data best, then you know it's probably 3 sterile neutrinos in nature.
Okay, I think we have time for one more question if there's anyone else left.
This is about magnetic monopoles that I think Robert mentioned. Are there any possible experimental signatures of that gradient theory monopoles?
No, I don't know. That is experimental is very hard to find. These are very heavy monopoles. First of all, you cannot produce them. What you could measure magnetic monopoles from the sky, but so far that has been unsuccessful. So, yeah, no. I think there was one event, Cabrera in the 80s or something, but just a single event. Or there is how is they produce. You see, they produce some electric some current. They go through a so I don't know exactly the experiment, but yeah.
Okay, thanks for everyone who was able to either be here in person or join online. If we could thank our speakers one more time, that'd be great. And just a reminder, this talk will be available to view and share using the same link you received online, or if you're here in person, institute.surf/deeper-talks. We'll have a recording of this available. Next month's Deeper Talk will be on August 14th at 9 a.m., and the topic will be focused on the deep underground neutrino experiment in particular. And we're going to end, there'll be a QR code showing on screen and online. We have a quick survey. We'd appreciate if you can fill that out, so because this is a new program for us and we're trying to improve it as quickly as we can. So any feedback's appreciated. Thank you and have a great day.